Good afternoon. Today we will be talking about memories. Earlier we talked about read-only memories as a part of combination logic design. We talked about PROM, PLAs and PAL, said they can be used in design of combination logic. The ROM is a read-only memory, ROM, read-only memory. Which means basically means read-only memory means you can read what is stored in the memory, the content of the memory, but not alter it. Does not mean that you cannot change it. You can erase in program. So, when you say PROM, it is a programmable read-only memory where you can put the content, change the content. Before that you want to erase the memory, you can say EPROM. Erasable programmable read-only memory. The different types, but generally these are used for storing information which does not change. Like in a calculator you want to have a ROM or PROM to, for example, store tables. You want a sine value, cosine value for any given angle, the value will be stored there, you can just recall it and use it as an example this. But for storing data as we go along and reading and writing, these are called RAM, random access memory. Also known as read-write memory. These are non-volatile memories, which means when the power goes or power is removed, the content of the memory does not change or disappear. These are volatile memories, which means when you switch off the power, the content is erased, and when you use it again you have to write again the content. These are used for, as I said, this is used for storing values does not change. This is used for storing values which keep changing in a program, something like a scratch pad. Sometimes it is called a scratch pad memory. We have already seen ROM, PROM, erasable ROM, all that earlier when we were discussing combination logic and how to use memories, read-only memories in that. But at that time we did not talk about this. So today we will spend our time talking about random access memories or read-write memories. Basically, you have a memory means the following things are required. This is memory. or RAM, you have address lines, multiple address lines, how many locations are here. Based on that, you decide the number of address lines required. Suppose I have address line, let us say 8 address lines. That means I can store 2 power 8, 256 locations. Then I put data in. In each of these 256 locations, I can write the data, which can be width of the data, size of the data can depend on the number of words, number of bits each of the locations have. Let us say 8 bits. So, there will be 8 lines which will be used to write data into these 8 locations of every, these 8 bits of every location. So, this is 8 bits and this is one of 255 locations, 0 to 255 is 256 locations. Each of these locations I can write a word of 8 bits. Then I should read the data also, because it's a read-write memory. I can write information using data in lines, and I can read information that is stored using data out lines. Then there is usually, you should know whether we are reading or writing. So I need a line called read write. Read, if I am going to read or write, I should know, the memory should know whether I am going to read from one of the stored locations or write or change the content of one of the data locations. So I should have read or write. So this is how a memory is organized. Let us assume in general there are k address lines. K address lines will have 2 power n locations.
It has been built much faster than conventional buildings. In just 1 month,
2 power k locations, 2 power k locations.
It has been built much faster.
Each of these locations we can have,
in just 1 month.
let us say n bits word, and I can read those n bits. And there is a signal called read or, see, the memory should know whether you are reading or writing. Usually there is a single signal called read write bar. If this is 0, it is 0, you write into the location. It is 1, you read from a location. So instead of using 2 lines, one for read and one for write, we use a single line called read write bar. If it is 1, I will read from the location chosen by this address all the n bits, and write, if it is 0, I can write into this location located by the address lines an n-bit data, and it will be retained there. And then there is usually another signal called select signal or enable signal, memory enabled. Only if the enable is high, if enable is 0, whatever we read or write, no activity. No operation. Enable is 1, if it is 1, I read the memory. Enable is 1, it is 0, write into the memory. This is how a memory works. Usually a memory also have 2 more registers. I will put it outside this, or maybe I will redraw the circuit. The address does not directly go to the memory. And this is called memory address register. And the data that is coming out usually stored in a buffer called MBR. MBR stands for memory buffer register, which takes the value which is read, because the circuit which you should give this value may not be ready to receive it. So as soon as you read it, it goes to the memory buffer register, held there till it is used. Similarly, with the address register you give, address may change, address may disappear. So I want to store it in the MAR till I am able to use this to decode my location, memory location. That is how it is. So as I said, there are n lines and read write bar, as I said. And enable. Data out. Data in. This is my RAM. Actually, it's a read-write memory. Random access memory means you can access any location the same amount of time. It is not serial. Supposing you are looking for data from a magnetic tape. Supposing you have stored the data in a magnetic tape. To locate the data, you need to wind the magnetic tape to the point where the data is stored. On the other hand, that means that the amount of time to search for the data depends on the location in which data is stored. So non-constant, the magnetic access time for data varies in magnetic storage. Whereas access time is constant for random access memory, because wherever the data is, it takes the same amount of time to get to the location. That's why it's called random access memory. So suppose you want to read data, or first let us say, yeah, read the data from memory location. You need a This is called memory read cycle. When you want to write the memory or write into the memory, memory write cycle, again you have a clock. As a function of time. Let's call this T1, T2, T3, T4. I think I don't have to show this. Then here I'll again place the address from which I want to write the data. Address will change from what it was originally to a new value from into which I want to write, and that is kept here like this. This is the address. Then I indicate it's a write operation, so a read write bar will be negative now, I mean low. or it will go a little higher earlier. And again I have to memory enable. Zero to 1. Then I place the data. I want to write the data into location. So I need to place the data and keep it till almost the end of T3, and the actual writing takes place here. Instant at which write takes place. When the read write signal goes 0 to 1, at this point in time, whatever data you put will be written in the location given by this address. This is the read memory write cycle. Now we said there are two types of memories, read only memory and read write memory. We are discussing read write memories, where memory can be used to write as well as to read from. Whereas the earlier memories we discussed during the combinational logic design, the read only memories where the information that is stored will be used for the design, but it cannot be altered unless you remove it from the circuit, erase it and reprogram it. Now, there are types of read write memories. Types. As I said, sequential, usually magnetic tape, any magnetic material for storage. You can use magnetism to store data, which for that it goes sequentially. So the access time is not constant. The one we are talking about is semiconductor type. This is random access in the sense wherever the data lies, it takes about the same time for accessing it. That means there is a proper decoding system which we will discuss. Within this, there are two types of memories. One is called static memories, static RAM, the other is called dynamic RAM. Static RAM and dynamic RAM. Static RAM uses latches and flip-flops. Dynamic RAM uses charge of a capacitor. To store information, it uses a charge of a capacitor, charging and discharging. That is how you read and write. Here it is latches or flip-flops where you can read or write, as we have seen earlier in sequential circuit design. Now as you know, no capacitor can retain the charge forever. Charge will slowly decay, leak. So every once in a while when you are using a dynamic RAM, you need refreshing the memory. That means I cycle through all the memory locations so that the original charge of each capacitor is restored. So this is called refreshing operation. Refresh of dynamic memory, DRAM, cycle through each location to restore the original value. How often do you have to do it? Depends on the type of memory you are using. It used to be a few milliseconds, nowadays technology is better. A few to a few tens of milliseconds. Few milliseconds or few tens of milliseconds. So it is not very easy to use. When you use a dynamic RAM, I should also provide a refreshing circuitry. Design should include refreshing circuit. But why do you use it? Because it is cheaper and has higher density. For a given area of semiconductor, I can put more locations of a DRAM compared to a static RAM. And as I said, since it is only capacitor charging and discharging, it tends to be cheaper, whereas here it is the flip-flops and latches. But for convenience, sorry. But for convenience of use, we will use SRAM. SRAM is more convenient. And nowadays, it is not very expensive because memories have become very cheap. Not very expensive now. Unless in huge systems. If it is very huge system, then the cost will prohibit the use of cost and the space. The cost and the space will prohibit the use of SRAM. We will go for DRAM. Otherwise, normally for most of the applications today, we will use SRAM. So we will see what is inside an SRAM. I said it is a latch or flip-flop.
on the timing diagram,
Ah.
you have explained address
Ah.
and data line, address and data line and
Ah.
read write line.
Ah.
On that, when the data is changed at the time of write cycle, after again it is changing. How it is again explain that clearly.
See, we do not know the address, I am just giving a typical diagram. The idea is from one address to another address. We do not know what is the previous address, what is the, I may be reading from one location, let us say location A. See, I am reading from a location A now, that is the address for A, that is over. Then I will change it and then read from location B. So I am only explaining one. So I am going to explain to you, I was explaining to you what is the procedure for reading from location B whose address is given. We do not know what the previous address is, we do not know, I am just putting it as an example. There may not be anything here. I have now taken, maybe there is no reading, or in that case you put a 0. Because we are assuming the memory is constantly being read from one location to next location to next location. So the address location A, all this procedure was completed, and address location B, I am giving the address, and then the read write line, let us say write. Then we will say memory enable, and I put the data. Again there may be the previous data which has to be changed and a new data has to be put here. That is all I am saying. And when we do that, new data, let us say new data to be written in location B. So at that time the write line will go from 0 to 1, at that time this data will be written in the location B. And then again there will be another location, location C address. This is only a typical diagram. This is the way timing diagrams are drawn in books and data sheets. Does not mean anything. All you have to understand is only this part. Address is first given. I do not know what is the value of the address, so I am putting like this. There can be zeros and ones because address is not a single line. Address is a multiple line. So some of them are 0, some of them are 1. So I put like this, whereas zeros are also there, ones are also there. Location B has some zeros and ones in their address, in its address. That is together shown like this, with something on the top, something at the bottom. In that location B, you want to write something, you have to enable the write signal, enable the memory, and you have to place the data which will be written into that. This is typical diagram of, we are only interested in location B. What was happening before in location A or what is going to happen later in location C, we do not know. That is why we show like this. What is the previous address, we do not know. What is the current address, we do not know. What is the next address, we do not know. How many zeros are there, how many ones are there, we do not know. This is how it is done. Is that clear?
Yes, sir.
Okay, thank you very much.
Thank you.
Dinesh, I am muting you now.
Okay, what is inside? Because we said volatile memory, non-volatile memory. Non-volatile memory is the PROMs, read-only memories, where we store data and use it. You want to change it, you erase it and reprogram it. That we discussed in the application of combinational logic. Then today we started about read-write memory, where we can read and write and the power dissipates. It is called volatile memories. When the power disappears, power is taken off, whatever you have written disappears. There we said reading, writing, address lines are required. Read, write, whether we are going to do a read operation, write operation should be told to the memory, and we should give the data input and data output, so memory enable. Then we saw the timing diagrams for both read and write. Then I said there can be two types of read-write memories. One is sequential, which is not used normally. Of course, these are used for backup and all that. In system, when you are using memory as you use, like a microprocessor, you use static memories, which are semiconductor memories. These are random access because the reason is whatever is the location, we can access it the same amount of time. And there are two types of semiconductor memories. One is static RAM, the other is dynamic RAM. Static RAM uses latches and flip-flops. Dynamic RAM uses capacitor charge storage, but capacitor being a leaky device, you have to keep refreshing it by cycling through all the locations each time. It depends on how often you have to do, depends on the technology today. A few milliseconds to a few tens of milliseconds. Design should include refreshing circuitry, so design is a little complicated, but it is cheaper and has higher density. That is why we use it, even though the design is a little more complicated. But SRAM is straightforward and easy to use, more convenient, not very expensive, because today memory prices have fallen down, but you want very huge systems memory, then you won't use it, you will go for this. So now I will show you what is inside a static RAM. So we will call a memory cell, a static memory cell, call it MC. MC stands for memory cell, static memory cell. We have address, input, output, you have to select this cell. And you have to say whether you are going to read or write. How does it look like inside? We have an SR latch. With two AND gates. You know, when SR with S and R inputs being complementary becomes a D flip-flop. We have seen this earlier. So this is the data in. Then we have to select this, only then we can write this. So we have to have a select signal. It goes into this and this. and the data comes out, also again we have to select this. But whether you are going to read or write depends on another signal called read write. So it is read, so this completes the design of a single memory cell. This is Q. Take an SR flip flop or a D flip flop. Instead of this I can also put it as a D flip flop. The D or an SR latch. This inverter is to make sure that data input is applied as 0, 1 or 1, 0, because 0, 1 will set the flip flop, make the input output 1, 1, 0, 0, 1 will make the output 0. So I need this, but there will be similar cells all over the memory. What is, how do we know only this cell we are addressing and this cell is what we want to read from or this cell is what we want to write into? That is done by a selection mechanism, but we will show you separately that selection mechanism will come and select these AND gates. And finally, Q can be, I may be putting data into this memory or reading from memory. If it is 1, I will read it. If it is 0, this will go into this AND gate. So this AND gate will be disabled because it is a 0, it is a write operation. This will be, the selector has to be selected, this will be 1, this is 0 or 1 depending on whether we are storing a 1 or a 0. This will be 0 if you are writing, in that case the output will not come. If it is 1, if it is a read case, in this case output will come. So opposite of that, the complementary of this is applied to this. If it is a read operation, this will be enabled, selector, the data will be enabled, this will go into SR. If it is a write bar, read, this will become 1, this will become 0, so nothing happens. So write, this is 0, this is 1, so these two gates will be enabled on the mechanism. So putting a data into this means writing operation, reading from the data is read operation. When it is a writing operation, these two gates will not work because of the input here, and if it is a read operation, if it is a write operation, this will be put as 1, this will be 1, data will be either this or this, either it's a 1, 0 or a 0, 1, and in either case we should select these cells. This is a cell details of a SRAM cell. What is inside an SRAM cell? And like this, many cells are there in a memory. How it is organized? First of all, how do you know, for example, the memory? Let us say 3 address lines. There are 8 locations, and then let us say 4 data input. These memory cells will be like this: 1, 2, 3, 4. Each is a cell. Like that, there are 8 rows. So 8, because the 3 address line, there are 2 power 3, 8 address locations. Each address location will have 4 data points. So 4 cells. So this is 8 times 4, 32 cells will be there. And each of these cells will be like this. This is what it is, symbol. This is what it is. Now how do we know which of these rows is going to be located for reading or writing? For that we need a decoder. So in this case we need called decoding of address lines. The select lines we drew there will come from a selector line now, 3 address lines. So 3 times 8, 3 to 8. Decoder. So this will be 8. So each of them will go to the, we will call these words, actually this is word 0, word 1, word 8, word 7. 8 words, each of 4 bits. So now this is the selector line for word 0. This is selector line for word 1. This is the select line for word 7. So this is what this line is. This line is nothing but this. So when we are selecting this 7th row, this cell will be activated. All the 4 cells of this 7th row selector will be activated so that we can write into these cells or read from these cells. And read write signal will make sure of whether it is reading or writing because of this logic here. So to want to make it simpler, we will make a 4 address lines, 2 address lines, 4 by 4 cell. Now let us say example 4 by 4, that means 2 to the 2 times 4, that is 2 address lines, this is word 0, word 1, word 2, word 3. Now these select lines first word 0, select 0. This will be connected to all the 4 cells of the row 1 of the word 1. These are the 4 cells. Data input. It will be different for each cell. Input bit 0, input bit 1, input bit 3, input bit 2. This goes into this, this goes into this, this goes into this, this goes into this. Now, read write. Including the logic that we have shown, this logic. That will get this line into read write. I can either read or write, not both at the same time. So I am reading. So this is read write line. A typical memory organization is what I am showing. We are selecting word 0. That means all the 4 cells of word 0 will be selected. We are giving input to this for reading, for writing. So input to input 0, input bit 0, input bit 1, input bit 2, input bit 3. We are reading, writing. So in this case we are writing. So that read write signal will go here, and then the output data will come here. In this case there is no output because we are writing. So this is input 0, this is out bit 0, out bit 1, out bit 2, out bit 3. This is a typical data representation in a memory, how to memory is organized into rows called words, and each word will have columns corresponding to the number of bits. If it is a 4 by 4, there will be 4 words and each will have 4 bits. For that I need 2 address lines. In this case I use 7, that is why it is 3 address lines. There are 8 rows, word 0 to word 7, each with 4 bits. This example we have only 2 address lines, word 0, word 1, word 2, word 3, and this goes into this. Now, you can go on. This is only a sample example how to do this. So any memory, supposing I have a 1K memory. K bytes. A byte is 8 bits, which means there are 1024 locations of 8 bits. So we will have 10 address lines This will have 2 power 10. Word 0 to word 1023. Then it goes into the array here as I shown earlier. Data in 8 bits because I said bytes. Get out and read write. Memory select. These are the select lines. So this will have 1034 times 8 cells. But then as the number of size of memory increases, 2K bytes require 2048, 4K 4096. So it keeps on increasing, so the decoding is going to be more and more difficult. For this itself, we want decoder. A decoder will consist of 10 address lines. This decoder will have 1024 AND gates with each 10 inputs. This is too much. This will require, for example, 4096 AND gates with 12 inputs. This goes on and on. To avoid this, we have what is known as a two-dimensional addressing. You split this into two. 1024 means 10 address lines. I will make this into 2 power 5 times 2 power 5. 2 power 5 times 2 power 5 is 2 power 10, which is 1024. So I have 2 power 5 address lines or 5 address lines. Which will require only 31, 0 to 31, 32 AND gates, 5 inputs. These are called row address. Then I have a column address. The other 2 power 5 I will put here. So this will have 0 to 31. So this will have 32 AND gates with 5 inputs. Now, this is 1024 AND gates with 10 inputs each. Here I have 32 AND gates with 5 inputs, another 32 AND gates with 5 inputs. That will be 2 times 2 into 32, 64 AND gates with 5 inputs each. Drastically reduce size. That means my memory will be organized as a 2-dimensional memory. 1024 is organized as 32 into 32, 32 rows and 32 columns. So this is 32 rows, each one will be 32 columns, and like that each of these will have as many bits as you want, 8 bits or 4 bits or whatever. So the whole memory is organized into a 2-dimensional memory. It is called 2-dimensional memory, which will split the address into 2. 5 lines are called address row addresses. Another 5 lines are called column address. So row address will be decoded as which row is the memory cell we are talking about, and then in which column it is, and that chosen location, let us say this is chosen location, will have as many memory cells as required in the number of words. Suppose it is a 1K bytes, each location will have, chosen location will have 8 bits or 8 memory cells as we described earlier. This is much convenient. Also speed wise it is faster, because instead of searching one location out of 1024 locations, the time taken is much more than trying to locate one of 32 here, at the same time one of 32 here. They work simultaneously. One of 32 here, this location and this location, they work at the same time. So it is going to take the time required to select one of 31, one of 32, another one of 32. That is much faster than, so the speed wise it is faster. Hardware wise it is much better, because the number of AND gates in the decoder will be only 64 and each with 5 inputs, whereas here it is 1024 each with 10 inputs. So time taken is also lower. So this is called 2-dimensional addressing, and this is for larger memories, this is what is done. Sometimes even that we find is too much. It's called multiplex addressing. Multiplex addressing means instead of all the 10 addresses will be taken, but first only row address will be used and then the column address. So multiplex addressing. you take, let us say 256 by 256 array. So what we will do is, first 8 bits we will give here, 8 bit address, row address, and decode it 8 into 256, and we will locate this decoder. This is row address register, this is decoder. We will give a symbol called row address selection, RAS. Then we will have 8 bit column address, eight-bit decoder, 8 into 256 decoders. This is called column address selection. First we will give this address, then we will give the same address lines we will use to give this address. The idea is to not have 256 by 256 will require 16 address lines. To reduce the number of pins required in the chip, we will use 8 bit first, store it in this, call this row address, the same lines we will use to give the column address, and then this enable them by what is known as a CAS, column address selection. So first we will select this and then they select this, and together they will be applied here, and of course with the data read and data write and all that, data in, data out. This is a case where the number of address lines is huge. This is only an example. 16 address lines is not too much. Suppose you have a large memory whose address lines are not much more, instead of having so many pins to just give the address to the memory, we will divide it into two parts, row address and column address, because this organized as 256 by 256 by a matrix, like in this case. In this case also we had a matrix. Of course, we here use 1024 only, 32 by 32 matrix, whereas here it is 256 by 256 matrix. First you give the 8 bit address corresponding to the rows. Using the row address register, you store it and decode it and apply here. Then the same lines we will use to give the column address, decode it, and then together they will be applied here, so that which row and which column is selected, and that in that is either read or write, and each of these rows will have multiple bits as we did here. All the bits, 8 bits can be 32 bits, 16 bits, and read write is required. So there are so many devices, so many types, or so many ways of addressing memories and decoding them and using it. I will stop here today. In fact, I wanted to finish my lectures today, but it looks like I have to take one more. Next Wednesday, next Monday, which is 29th of April. I will take my last lecture where there is one more memory design example I will give you. Then I will give you some information about the logic gates and then give you the concluding lecture. So, next lecture 29th April will be my concluding lecture where I will finish this memory by giving you one example of how to design a memory system. Then I may give you some information about logic gates practically when you use them, what you have to look for, and then conclude the lecture series. If you have any questions you can ask me. I finished and you can unmute if somebody has a question. I have also decided to have one more lecture. I announced next lecture which is 29th April will be my last lecture where I will give an example and do some more things. Are there any questions?
The DRAM has higher density means higher amount of memory, sir.
It is not clear what you are saying.
This is DRAM has higher density. It is cheaper and has.
Yeah, I did not say fast. DRAM has higher density because the capacitance is much smaller compared to a flip flop. So, I can put more in a given memory space, and also because of the same reason it is cheaper. Okay, thank you, and tomorrow next Monday will be the last lecture, 29th. Okay, 29th April, not this Wednesday. Okay then, see you.